Have you ever stopped to wonder what makes a giant steel bridge strong enough to hold thousands of cars? Or how our own bones can handle the force of running and jumping without snapping? Well, it all comes down to something called the mechanical properties of solids. So today, we're going to dive into the physics that explains how all the materials that build our world respond to forces and, how they manage to bend without breaking.
Okay, here's how we're going to break it down. First, we'll challenge the whole idea of a rigid object. Then we'll get into the two most important words for today, stress and strain. After that, we'll look at the laws that tell us how materials actually behave, figure out how we measure their stiffness, and then see it all come together in some really cool, real-world engineering examples before we wrap everything up.
All right, let's kick things off with a core idea that, honestly, we usually just take for granted. We have this picture in our heads of solid things being perfectly rigid, but the reality, it's so much more interesting than that.
So let me ask you, are the solid objects all around you, your desk, your phone, are they truly unchangeable? Well, the answer might surprise you. It's a big no. The truth is, even a thick steel bar can be stretched or squashed or bent if you apply enough force. And that's a huge insight right there. No solid body is perfectly rigid. They all deform.
No, this ability to deform and maybe spring back is described by two key properties. First up, you've got elasticity. The best example is a spring. You stretch it out, and when you let go, it snaps right back to its original shape. That's elastic behavior. Then, on the flip side, you have plasticity. Think about a lump of putty or mud. If you squeeze it, it just stays squeezed. It's permanently deformed. And getting this difference down is absolutely crucial for everything that follows.
Okay, so if we want to get scientific about these deformations, we need to speak the right language. And that language is built on two fundamental concepts, stress and strain.
So, first on deck is stress. We use the Greek letter sigma for it. You know, when you push or pull on something, the material itself develops an internal force that pushes back, trying to resist that change. Stress is just that internal restoring force divided by the area it's acting on. And this is super important. It's not just about how much force you apply, but how that force is spread out.
Now, wherever you have stress, you're going to have its partner, strain, which we represent with epsilon. You can think of strain as the measure of how much the object actually deformed compared to its original size. So, if we're stretching a wire, the strain is simply the change in its length divided by its original length. And get this, since it's a ratio of two lengths, say meters divided by meters, the units just cancel out. So strain is a pure number, it has no units.
Now, it turns out there are a few different flavors of stress and strain. When you pull on a cylinder like this, stretching it out, or you push on it to compress it, that's what we call longitudinal stress. And, you guessed it, the change in length it causes is the longitudinal strain. The key thing here is that the force is applied straight on, perpendicular to the cross-section.
But what if you apply the force parallel to the surface? The best way to picture this is pushing the top cover of a thick book sideways. This is called shearing stress. You're not changing its length or its volume, but you are changing its shape, making one face slide relative to the other. That resulting change in shape is the shearing strain.
And then there's a third type, hydraulic stress. Imagine you take a ball and sink it deep, deep down in the ocean. The pressure from the water is pushing in on it from every single direction, right? It's being squeezed uniformly. This squashes the object, making its volume smaller without changing its geometric shape. Here, the stress is the pressure itself, and the change in volume gives us the volume strain. So we've got stress, that's kind of the cause, and strain, the effect. The big question is, how are they connected? Well, it turns out that for most materials, as long as the deformations are small, there's a really simple and powerful rule that links them together, and it's called Hooke's law.
And this rule is Hooke's law. Now, this isn't something someone figured out with pure math. It's an empirical law, which just means it's based on tons of real-world experiments and observations. And all it says is that for small changes, stress is directly proportional to strain. It's that simple. If you double the stress, you're going to double the strain. The number that connects them is called the modulus of elasticity, and it's basically a measure of how stiff that material is.
Okay, this graph right here, it's like the life story of a material under load. Let's walk through it. Starting at O and going up to point A, it's a perfectly straight line. This is where Hooke's law is in charge. If you let go of the force anywhere in this region, the material snaps right back. But past point B, the elastic limit, things get interesting. From B to D, we're in the plastic region. If you let go now, it's permanently stretched. Point D is the ultimate tensile strength, the absolute most stress it can handle.
After that, it starts to get weak and thin out, until it finally breaks at point E.
So let's go back to that constant from Hooke's law, the modulus of elasticity. It's a really big deal. It's a fundamental property of any material, and it turns out we have a specific modulus for each of the 3 types of stress we just talked about.
All right, so here they are, the big 3. First, you've got Young's modulus, which we call Y. This is all about how much a material fights back against being stretched or squished. Then there's the shear modulus, G, which tells you how much it resists being twisted or having its shape changed. And finally, the bulk modulus, B, measures how well a material stands up to being squeezed from all sides.
Now let's take all this physics and see where it pops up in the real world. And for our first example, we're going to the circus. Seriously, this is an awesome example of Young's modulus at work. Okay, so picture this, a human pyramid. You've got that one performer right at the bottom holding everybody else up, right? In this specific case, imagine the total mass being supported by this person's legs is a whopping 220 kilograms. That is a huge amount of compressive force pushing down on their 2 thigh bones.
So here's the question. How much does each of those 50-centimeter long thigh bones actually get squished under all that weight? Well, if you plug in the numbers and use the Young's modulus for bone, you get an answer of just 4.55 times 10 to the minus 5 meters. I mean, that is tiny. It's less than 1/10 of a millimeter. It's an incredible demonstration of just how unbelievably strong our bones really are.
And look, this isn't just some cool circus trick or a random fact. Understanding elasticity is absolutely fundamental to pretty much any kind of engineering you can think of.
I mean, think about one of the biggest engineering challenges out there. Building a bridge. That thing has to hold up its own massive weight, plus all the cars, all the trucks, and it has to stand up to the wind trying to push it over. To pull that off, you have to be a master of elasticity.
And that's why we have brilliant designs like the I-beam. See, when a beam bends, most of the action, the stress, is happening at the very top and the very bottom. The stuff in the middle, it's kind of just along for the ride. So the I-beam is genius. It puts the metal where it's needed most, at the top and bottom, and gets rid of the heavy, unnecessary stuff in the middle. You get maximum strength from minimum material. It's a perfect application of these principles.
Okay, wow. We have covered a ton of ground today. So let's do a quick fire round, a recap of the key things you absolutely need to remember.
All right, so the big ideas. Stress, that's the internal force per area. Strain, that's the fractional change, how much it deforms. Hooke's law, for a while stress is proportional to strain. Remember the stress-strain curve, that's the whole story from bending to breaking. And finally, the elastic moduli, Young's, shear, and bulk, are how we put a number on stiffness. All of this, as we've seen, is totally critical for building, well, everything.
So, the next time you cross the bridge or even just stand up, remember this. Elasticity isn't just some chapter in a physics book. It is, quite literally, the science that holds our world together. It explains how things can be strong and yet flexible, and how they endure incredible forces every single day. Ultimately, it's the science of building a world that can bend without breaking. Thanks for watching.